So today we will be learning about acid and base. So this is maybe the topic you guys requested. So continue this. So today we will learn about the pH scale of acid and base, and we will learn what acid and base are in chemistry, what strong and weak acid and bases are. We will learn about the litmus paper test. We will learn about neutralization reaction and chemical equation, learn about the periodic table, and the valence electrons and ionization. So here are some examples of acid and bases. So you can see a lot of things maybe you guys can notice. So in the middle, we have water. Water is exactly in the middle, so it's called neutral. But if you move a little to the left, we have the acids like milk, apples, and oranges. All of those are acids. But on the right, there are examples of bases like soap, bleach, ammonia. All of those are examples of bases. But let's look at what bases actually are. So bases seem to have a high pH scale on the right, the higher number, and acids tend to have lower ones, lower than 7. Here are some properties of acids and bases before we get into the proper definition. So acids are when pH is less than 7. So it's less than 7. So all of these are acids. And then it turns the litmus paper red. It tastes sour. So if you guys have tasted oranges before, you can tell that oranges are very sour or lemons. So that's a taste of sour. It's a property of acids. And it feels irritating, corrosive. And yeah, examples are fruit juices, soda, and coffee. And then on the right, we have bases. It's when the pH is greater than 7. So from here all the way to the right. So all of these examples are bases. All of these are acids. Bases turn the litmus paper blue. We will actually see a video about this. Pretty interesting. But it tastes bitter or soapy. Those are bases. And it feels slippery. And examples again include baking soda, ammonia, and soap. And down at the bottom, I've written down a small neutralization reaction. And we will look at this in detail a little later. But basically, what it is that you're adding acid and a base, a strong acid and a strong base, to create salt and water. But let's get into the proper definition of what is an acid. So you guys might have heard the term acid before, but the definition can be a little bit confusing. But an acid is a chemical that gives off hydrogen ions when dissolved in water. So it has the property to give off its hydrogen ion. So again, acid have a pH below 7 and taste sour. We know those are properties of acids. And here are some examples of acids. And you can notice there are some similarities. It has an extra hydrogen attached in almost every single one here. So you can see that HCl, this one, for example, it gives off a hydrogen ion and a chloride ion when it's in water. You can see in the picture on the here left. When HCl is dropped into water, it's liquid, it gets separated into hydrogen ion and chloride ion. So that's why it's called an acid. And it can also be written as like this. This is just the, in considering the adding the water. But all of these, all the acids give off hydrogen ions when in water. And bases, on the other hand, can accept hydrogen ions or release hydroxide ions in water. But bases usually taste bitter, feel slippery. We've learned these are properties of bases, pH greater than 7. And examples are these, all of these. Sodium hydroxide, NaOH, calcium hydroxide, CaOH2, ammonia, NH3, potassium hydroxide, KOH, and magnesium hydroxide, which is MgOH2. Similarly, you can notice some similarity between all these. We have OH, 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 but ammonia seems to not have an OH, but it's still a base because it accepts a hydrogen ion. A hydrogen can be added. So let's look at an example of hydroxide ion, sodium hydroxide here inside of water. And you can look at the diagram on the left too. When you drop sodium hydroxide into water or liquid, it separates into sodium ion and hydroxide ion. You can see on the equation on the right too, NaOH is a base. It separates into Na or OH, but this is really temporary because since NaOH accepts an hydrogen, hydrogen is automatically added to hydroxide, and then it just simply equals H2O, which is water. So you can think about bases as accepting hydrogen or temporarily giving off this hydroxide ion. So again, bases can accept hydrogen ions or release hydroxide ions. You can think of it either way. So sodium hydroxide, we learned it becomes Na plus H2O because OH adds a hydrogen ion there. And ammonia, you can see that it's NH4 plus when hydrogen ion is added, and so on. And these are all examples of bases. So let's look at ionization of acid and bases all together on this slide. So HCl, we've seen it dissolves into H plus Cl minus. It's pretty straightforward. And we have H2SO4, which turns into two hydrogen ions and one sulfate ion. So it's SO4 2 minus, and we have HNO3, just one hydrogen ion and one NO3 minus ion. So you can see that hydrogen, all of these are separated when they're in water. And you can see on the bases, NaOH, when it's in water, separates into Na plus OH minus. And then you can see patterns with other ones as well. KOH separating into K plus and OH minus. Similarly with calcium hydroxide 2, separating into calcium and hydroxide ions respectively. And same with magnesium and this very bottom as well. It's a mix of sort of ammonium and hydroxide ion. But you can see a pattern here as well, right? In bases, hydroxide ions tends to be released, but on acids, hydrogen ions seem to be released. But again, there are some exceptions, especially to the base. The more formal definition would be a base accepts hydrogen ion, but most accepting hydrogen ion bases have a hydroxide, have an OH. That's why we can put it this way. And I think most of the questions you will see in the BEC exam, those will contain OH. Whatever contains OH would be a base. And whatever has kind of H in front separates into hydrogen ion and another anion, then it'll be an acid. So remember these two. Okay, so we can briefly talk about strong and weak acids and bases. So this will be only important when we're talking about, neutralization reaction and pHs. But strong acids and bases, just know that it completely dissociates in solution or water. So HCl was an example that we looked at, completely separates into hydrogen ion and chloride ion. But we also have NaOH, sodium hydroxide, which we looked at already. It separates into sodium ion and hydroxide ion. Since they completely separate, dissociate into ions, they are called strong acids and bases. But there are also weak acids and bases. But what are weak acids and bases? They only partially dissociate in solution. So they don't completely dissociate to their ions. It's only a couple of them. Examples are this acid, acetic acid, and we also have ammonia adding to water. All of those are examples of weak acids and bases. But just know that strong equals completely dissociate. Weak equals partially, only small amount is dissociated. But let's look at this right here. So these are where the strong acids and weak acids and weak bases and strong bases are put in terms of pH. So pH scale basically shows us how much concentration of H plus there is. But so the lower pH on this side on the left means more H plus. So more H plus on the left, less H plus on the right. So let's look at some of these. We have strong acids on the very left. And this makes sense, right? Because strong acids dissociate completely. So it has a high on our high hydrogen ion. So that's why pH is low. Then we have weak acids. They partially dissociate. So it has this range of pH, still below neutral, because acids give off hydrogen, but it's weaker than the strong acids. It has higher pH than strong acid. And then on the right, after neutral, well, example like water, salt water, all of those are neutral. But on the right, there are weak bases and strong bases. So remember, weak bases partially dissociate into hydroxide. And what does hydroxide do? Does anyone remember? It accepts hydrogen, right? Hydroxide accepts hydrogen. So it's right, hydrogen concentration will be less for bases, but strong bases are more stronger. It accepts hydrogen better. That's why pH is high, higher for strong base. And weak bases, although it's higher than neutral, which is 7, neutral is always 7. Yeah, but it is weaker and lower in pH than strong bases. I hope, yeah, that makes sense for everyone. If you have questions, always ask me. Feel free to ask me. So, but here are some examples of strong acids and strong bases. Maybe it's important to know some of these. Like you can know HCl. That's a strong acid, hydrochloric acid. And maybe you guys need to know HBr and HI as well. So these are simple enough to remember, I think. So hydrochloric acid, hydrobromic acid, and hydroiodic acid. So HCl, HBr, HI. But there are other ones as well, like HClO4, perchloric acid, HNO3, nitric acid, and all the way bottom here, H2NO4, which is sulfuric acid. And on the right, yeah, I'll let you guys write down this. If you have a note or a piece of paper, you can write down the strong acids and strong bases on your notes. So just write all of these down if you can, or if you want to. But strong bases include lithium hydroxide. This is important to note. Again, sodium hydroxide, we looked at this already. Potassium hydroxide, we also looked at this. Calcium hydroxide, we also had an example. But there are some other ones that we didn't discuss, like strontium hydroxide and barium hydroxide. So these are some examples of strong acids and strong bases. There are six strong acids and six strong bases. And if it's not a strong acid or a strong base, it is very likely that it's a weak acid or a weak base. So if it's not out of six of these, it's probably weak. But I'll wait a little bit just to make sure everyone wrote these down. Um, it may take, yeah, I think all of you guys are done, so I think I can move on. But if you have questions, you can always ask me to go back. But let's move on to the litmus paper test. So, litmus paper is a pH indicator. So, it tells you what the pH is of the solution. So, you're wondering, what is the pH of this liquid? And what is the pH of this liquid? So, how can you test this? You can dip the litmus paper inside the solution. You're putting the litmus paper in the solution. And you can tell the difference between acids and bases. So acids on the left here turns blue litmus paper. It's initially blue and turns it into red, right? It turns blue into red. That's an acid. And on the right, there is a base. It turns from red to blue. Bases turn red litmus paper into blue. So, yeah, here is a summary. Litmus paper is a simple pH indicator that changes color. So, acidic solution which has pH less than 7, it turns the litmus paper red. So, blue litmus paper turns red in acids, but red litmus paper remains or stays red in acids. Examples of acids are lemon juice, vinegar, hydrochloric acid. All of these are examples of acidic solutions. And yeah, just if you want to maybe write down something, you can just say that litmus paper turns into red. So I will actually show you a video pretty soon that I'll be moving on to acids. So acids turn litmus paper blue. Acids are pHs greater than 7. So red litmus paper turns blue in at bases, and blue litmus paper stays blue in bases. Examples are soap, baking soda, ammonia, and sodium hydroxide. All of these are examples of bases, and you will observe that if you stick a litmus paper in there, it will turn blue. So I will actually show you guys a video that shows this litmus paper test. But before that, the neutral solution. So you might be wondering, what about neutral solutions where pH is exactly 7? Well, both the red and the blue litmus paper do not change colors. And examples are pure water and salt water. So let's look at this video. So we saw an example of a litmus paper test. So we saw that in bases, red litmus paper turns blue, and blue remains blue. And in acids, blue litmus paper turns red, and red litmus paper remains red. And in water, there is no color change. That means pH equals 7. So, yeah, let's look at some questions so you guys can answer. So, one of the properties of acids is that they, is it A, turn wet blue litmus paper red, B, have no effect on blue litmus paper, C, turn red litmus paper blue, or D, all neutral to litmus paper. Does anyone know the answer to this question?
It's A.
Oh, yes, that is right. Yeah, nice job. It's A. Because acids, we've seen that it turns blue into red. And if it also said red remains red, it'll also be a property of acid. So yeah, A is the answer. Now let's look at this question right here. Two unknown solutions labeled A and B were brought to a junior high school free class. It was observed that in solution A, red litmus paper changed color to blue, while solution B, red litmus paper retained its color. So, what could be the content of solution A? So, we're looking at solution A. And what is solution A? I've highlighted here. It says a red litmus paper turned into blue. So it's a red to, it's a red to blue. So here, what could be the possible solution? Is it a car battery fluid, which is a strong acid, a B, salt solution, which is neutral, C, baking soda, which is a base, or D, orange juice, which is acid?
The answer is C.
Oh, yes, great job. The answer is C. That's correct. And it's because it turns a red litmus paper into blue, and we have learned that bases turn red to blue. And bases also let blue litmus paper remain blue. So that's why the answer is C. Let's move on to this next topic for today. So we will learn about neutralization reaction here. So you might be wondering, what is neutralization reaction? What does it have to do with acids and bases? Well, neutralization reaction is when you combine an acid and a base. So there's acid, here is base, and then that equals salt and water. So this is the most basic neutralization reaction. And let's look at it more closely, what it is. So I have a video here, and it explains a neutralization reaction. So here is the video. Yeah, this video didn't have any sound, but you can see that in parts of this video, first, you guys can see this person had equimolar, mean equal amount solution of HCl and NaOH. HCl is an acid, NaOH is a base. So first, they added an indicator. So that's an indicator. And we also added an indicator to the base as well. So the indicator just shows whether it's an acid or a base. If it's more pink-like here, then its pH is low, it's an acid. If it turns purple, then its pH is high and it's a base. Now the cool part is that when you mix these together, see, he's pouring these together, it turns green. So this green solution actually indicates a pH of 7, which is neutral. So acids and bases are neutralized, and its final products are water and salt. And that's why it's called the neutralization reaction. The acid and the base each neutralizes each other. So let's look at some examples of neutralization reaction. So we have HCl, which is an acid, NaOH, which is also an acid, I mean a base. It forms then salt and water. But let's look at this component-wise. See if this makes sense. So it forms NaCl. And where does that come from? Well, it comes from bases Na. Whoop, I'm going to draw an arrow, Na. And Cl comes from this acid, hydrochloric acid. Here. That's how it forms salt. But where does water come from? Remember, acid and a base form salt and water. Well, remaining we have, let me make it blue. So we have H and OH here. So H and OH combined make water. So I hope you guys can see this in action. So it's the same picture on the right over here. H combines with OH, Na combines with Cl, then it forms water and salt. Below is just a description of what it is. So hydroxide ion H plus component, it's positively charged that binds to hydroxide ion OH minus, just negatively charged. And we have sodium ion and chloride ion. All of these are components that are involved in the neutralization reaction. So you guys can just know that where salt and water comes from. And once we do a lot of examples, it'll all start to make sense. So let's look at more examples. We have HCl and KOH equaling salt and water. So if we break it down, we have hydrogen ion and chloride ion from HCl, potassium ion and hydroxide ion from KOH, and water itself is just hydrogen and hydroxide ion combined. And then KCl breaks down into K plus and Cl minus. So you can see all of these remains the same, essentially. This is OH plus H plus. So these combine to be water, and these, chloride and potassium, combine to form salt. And salt, by definition, is combined from this cation and an anion. And then we can look at more examples here. HCl and CaOH2 turns into CaCl2 and H2O. And I hope you guys can see this. As HBr plus KOH turns into salt. Here in this case, it's KBr and H2O. So this whole thing is called a neutralization reaction. And that's because acids and bases are neutralized, and its final form is salt and water. Again, salt comes from here, and salt comes from here. And all of these are aqueous, meaning in water. So this happens in water. And it makes sense because all of these break down in water. Yeah, I hope this makes sense for everyone. If it doesn't, always feel free to ask me a question. I will be happy to happy to answer. But let's look at this BECE theory question. So this is a theory question, which means that it's a little longer. It's like a short answer question. And we've already looked at this. I think some of you guys remember doing this. But basically, we are asked that student who went to bed immediately after eating complained of stomach upset the next morning, and the doctor prescribed liver salt, which composition is this, NaHCO3. That's the liver salt. And it says, using a balanced chemical equation, explain how liver salt would relieve the student of the discomfort. So, we can look at this in a sense of a neutralization reaction. So, this student, the chief complaint is stomach upset, and that can be caused, well, by a lot of things, but we can tell that it's asking for a liver salt. And it's a base because it has NaHCO3. It can accept a hydrogen ion. Since we know liver salt is a base, we can tell that it takes part in the neutralization reaction of stomach acid. So stomach acid can cause this stomach upset. The acid in stomach is hydrochloric acid, HCl, but we ingested liver salt, this NaHCO3, which is a base. So this is the reaction that happens in our stomach. When we take, sodium bicarbonate, we have hydrochloric acid from our stomach acid plus sodium bicarbonate equals salt and water and some byproducts as well. So I hope you guys can see this. Salt comes from here, chloride and sodium. And water comes from, it actually takes one of the O here. It forms an OH and an H, so that's why it forms a water. And remaining, this is a byproduct of a neutralization reaction. So, but the main components are salt. This is salt, and this is water. So these are the main components, but there can also be a byproduct of, let's say, carbon dioxide gas or any other things. But the main purpose of this question is that you know how to set up a neutralization reaction. You know how that acid combined with a base turns into salt and water. And you are able to show that you know what it is and write down the equation. So this is I think one of the most difficult questions that was on the BECE 2024 exam. So yeah, I hope this makes sense. I know it can be a little confusing at first, but we're covering this today because we're learning about neutralization reaction. But yeah, let's move on to this next topic here. So I want you guys to actually be more familiar with balancing chemical equations. So I want some of you guys to try this out. So, but always remember that atoms are neither created nor destroyed in a chemical reaction. So we have 2H on the left, 2Cl on the left. What will be the number that goes here? Does anyone know the answer? So we have 2H on the right, 2Cl on the left. Left. All of these are on the left. But we have 1H on the right, 1Cl on the right. How can we fix this to make these equal? We can add a 2, right? Here. What if we add a 2 on the right side? Then this becomes times 2 times 2. Now the left side and the right side are equal. Okay, so we can try to look at the next question as well, which involves K2O turning into K plus O2. So what can be added to either side to balance the equation? So one of the ways that we can do this is by adding a 2 on the left to match the 2 oxygen on the right. That's why we added a 2. So 2 oxygens are okay. But then we added 2 K2. So it'll be 4K on the left, but only 1K on the right. So we have to multiply this by 4. And I'm going to go a little quicker this time. There are 2 oxygen on the left. So we need 2 oxygen on the right. But this turns into 2 magnesium on the right. So we need 2 magnesium on the left. And everything is balanced. Now finally, we have this. So we need 2 Cl on the left, on the right. So Cl's are equal. But then this turns into 2 Na. We get 2 Na. So we need 2 on the left. So it balances Na and Cl as well. So this is balanced. So this is balancing chemical equations. And yeah, I hope that makes sense for everyone. We are trying to make the number of atoms on the left side and the right side equal to each other. Now, here are some questions that involve balancing chemical equations. So first, if you're asked the formation of ammonia gas, NH3, from nitrogen gas, N2, and hydrogen gas, H2. So we have N2 on the left, H2 on the left, and these reactants form ammonia gas, NH3. So what can we do to balance this? Well, we add 2 on the right because we need 2 nitrogens on the right as well. Since there are 2 nitrogens on the left, we need 2 nitrogens on the right. And this actually makes the hydrogen 6 hydrogen on the right because there are 2 H3. 2 times 3 equals 6. So we have 6H on the right, but we have 2H on the left, so we need to multiply this by 3. This makes 6H on the left as well. And we have completely balanced this chemical equation. So that's good. And finally, let's look at one more example. I know this can be tiring, a little confusing, but I hope you guys can make sense out of this. So, formation of water, H2O, from hydrogen gas, which is H2, and oxygen gas, which is O2. So H2 plus O2 equals H2O. Well, this equation is not balanced, so we need to balance it. We have 2 oxygen on the left, so we need 2 oxygen on the right. So we add 2 here. We need 2 oxygen. But notice how this also changes the number of H. 2 or H instead of 2, since 2 times 2 equals 4. So we also need 4H on the left. So we add coefficient, this number of 2. And now we have 4H on the left as well. And everything is balanced. You can see 4H on the left, 4H on the right, 2O on the left, and 2O on the right. So does anyone have any questions about this? Or if anything is confusing for this, uh, you can ask me a question now or later as well. So if there are no questions, I'll be moving on to this final part. Um, I will cover more of the periodic table and the ionization. So let's quickly go over this. We've already covered this sort of 2 weeks ago, but a periodic table is a chart of all elements. Remember, it's arranged by atomic number, just the number of protons. And the table has rows, which are called periods, and columns, which are called groups. And elements in the same group have similar properties. Now let's look at this. So you guys all remember the periodic table, right? So we can see there is an increase in period. Actually, it's arranged a little bit wrong here. It should be periods down and groups to the right. But you can see that there is an increase of proton numbers as there is an increase of atomic number. So let's look at carbon, for example. The carbon is a good example. It has an atomic number of 6. That means it has 6 protons. And its atomic mass is 12. Now, let's look at um, another example, like this, AC. How many protons does this element have? Well, we can look at the atomic number. It's 89, so we know this atom has 89 protons. That is a very simple way to look at this, and an effective way. So let's have some quick practice with periodic table. So which of the following pairs of elements are in the same period in the periodic table? And remember that periods are as you go here from left to right. So on the left to right, these are same period. So let's look at A, B, and Al, boron and aluminum. So boron is here, aluminum is here. Are they in the same period? Let's see. So boron is over here, which is period 2. Aluminum but is in period 3. So they are not in the same period. But let's look at rest of these. H and Li. H is over here. Lithium is over here. Again, they're not in the same period. They're in the same group, but not in the same period. Let's look at B, E, and B. So Be, beryllium is over here. Boron, B is over here. Can you guys see this? There's a connection. They're in the same period, both in period 2. That's why this is the correct answer. It's going to be C, beryllium and boron. And even if you don't have a periodic table, you can tell that the numbers are right next to each other or close to each other. If it's close, it's usually indicative of the same period. So close number almost always equals same period, but not always. But since they are right next to each other, they are in the same period. So here I've included the first 20 elements of the periodic table. So first 20 is the usual amount of element that is typically used in questions. So 1 is hydrogen, 2 is helium, and then I'm not going to read all this, but you can see there's an increase of atomic number all the way to 20. So remember that atomic number shown at the top of each element is called the atomic number, and atomic number equals the number of protons. We've learned about this. And how can we tell the number of neutrons and the number of nucleons? Well, you can look at the atomic mass, which is down at the bottom here. Atomic mass basically tells you the number of nucleons, the number of protons, plus the number of neutrons. So if we look at carbon, for example, we're looking at carbon, for example. So the atomic number of carbon is 6. So number of proton is 6. Atomic mass is 12, near 12. So nucleon number is also 12. And nucleon is proton plus neutron. So we can tell the number of neutrons from this. It's simply nucleon minus the number of protons. So 12 minus 6, which is 6. So there are 6 neutrons. That is how you can tell the atomic number, the number of protons, neutrons, and nucleons in the periodic table. And you might be wondering, what is the number of electrons then? Well, always remember that number of electrons equals the number of protons. Unless they are ions, but so protons, since they have positive charge, and electrons, they have negative charge. So they remain where neutral state exists. So with positive charge and negative charge, it remains neutral. So we need same number of protons and electrons. Yeah, here we have example of carbon atom. We've talked about this. So 6 protons and 6 electrons, 6 neutrons, and 12 nucleons. So this is how carbon atom is arranged. So let's look at this BECE question so that you have a chance to solve it. So, which of the following elements has 4 electron shells? So this is sort of moving into a little bit of our next chapter, but before that, does anyone have any questions regarding periodic tables and, atomic numbers or atomic mass? It's a little bit of a review, but does this make sense for everyone? Okay, yeah, that's great. So let's get back to this question. So it asks, which of the following elements has 4 electron shells? So electron shells actually come from the period number. Period number increases as it goes down. So potassium has period of 4, aluminum has period of 3, and phosphorus has a period of 3, and boron B has a period of 2. So we can go back to this periodic table and we can see potassium K is over here, period of 4. Phosphorus is over here, period of 3. And what else was there? We have aluminum and boron as well. So let's point that out. Aluminum is over here, same period of 3. Boron is up here, which has a period of 2. Remember, period increases as it goes down by a row. Groups increase as you go by columns to the right. But only potassium has 4 period. So that is why it has 4 electron shells. Period number corresponds to number of electron shells. So the answer is A, potassium. So here I've also summarized some properties of metals, which we've already learned last time too, but it's a quick recap. So metals are usually shiny, good conductors of heat and electricity, and malleable, meaning they can be hammered into thin sheets, and they're found on the left side of the periodic table. And there are also nonmetals, which is on the right, and metalloids, or like semi-metals in the middle here. But this is all review, so let's quickly move on to this last topic for today, which is valence electron. So so valence electrons, what are these? Valence means the outermost. So valence electrons are electrons in the outermost shell of an atom, and they decide how atoms react. So I will actually, these are just all words, so I'll explain it better with a picture. You don't need to read all this. So let's not read the words and look at this picture over here. So the valence electrons are all the electrons on the outside. So over here, all of these are valence electrons on the very outside shell of an atom. And now comes the really important topic of a stable atom. So a stable atom has a valence electron of 8. And we can arrange this in this structure right here. First shell can hold up to 2 electrons. The second shell can hold up to 8 electrons. And the third shell can hold up to 8 electrons as well. So it has this 2, 8, 8 electron structure. Now let's look at an example, and this will make more sense here. So let's look at sodium and how sodium ions are formed. Remember, sodium has an atomic number of 11, which means it has 11 protons and 11 electrons. Now let's put it in the 288 structure. Let's try this out with 11 electrons. We can fill the first shell because it only has 2. So we can check 2 out. We can fill 8 in the second. Here. But we have 1 additional electron in the third shell. And since the third shell is the outermost shell, this 1 electron is called the valence electron. So if a question asks you, what is the number of valence electron in sodium? You can answer 1. There's 1 valence electron. And because sodium has 1 additional electron on the valence shell, it wants to get stable into this 2-8 structure. So how can it do that? Sodium tends to take out this electron. It wants to get rid of it. So once this electron is removed or gives off to another atom, then it turns into this structure, Na+. So this sodium, initially with 11 electrons, loses 1 valence electron, and now it has 10 electrons. And we can see this is very much balanced. We have the 2-8 structure. So when an atom loses an electron, it's called a cation, and it has a positive charge. Sodium is an example of a cation, because we've just seen that it tends to remove an electron. But let's look at another example. This time it's of chlorine. So chlorine. It has an atomic number of 17. So it has 17 electrons. Initially, it has 17. We can see there is 2 electrons in the first shell. That's fine. 8 in the second, and 7 in the third. You can tell that all of these add 2 plus 8 plus 7 equals 17. That's a way to check. But we can see chlorine atom has 2-8-7 structure. Can everyone see this? Has a 2-8-7 structure. Every atom wants a 2-8-8 structure. This is the most stable form. So what does chlorine need to do to make 2-8-7 into 2-8-8? It needs another electron. It wants another electron here. It has a strong tendency to gain a valence electron. So now on the right in chloride ion, it has 18 electrons. It got it from somewhere else, an electron, and now 18 has a 2-8-8 structure. So chloride ion is stable, and this is an example of an anion. So anion is when an atom gains one electron and it has a negative charge. So cation means losing valence electron. Anion is gaining valence electron. So I hope, yeah, this makes sense for everyone. Um, but yeah, this is a summary of cations and anions. So we've talked about cations having positive charges and ions having negative charges of ions. And all examples of cations are these: sodium, calcium, potassium, magnesium. All of these are cations. Let's look at the anions. Chloride, oxygen, hydroxide, and sulfate. All of these are anions. So anions have negative charges, so all of these have gained some electrons to form an anion. And all of the cations lost electrons to form the ions. So I think we have a couple more things to go. So let's solve this question, a really quick one. So which of the following ions is formed by a loss of 2 electrons? So we're dealing with a loss of 2 electrons. What could be the possibility? Is it A, Ca2 plus, B, S2 minus, C, K plus, or D, F minus? Does anyone know the answer to this question? I think I heard D, but D is unfortunately not correct. And
The
I heard,
answer is A.
oh, yes, great job. The answer is A, that's correct. And the reason for this is that it lost 2 electrons. So calcium, as it loses 2 electrons, becomes Ca2 plus. So 2 electrons are gone away. Since electrons were negatively charged, when an atom loses an electron, it becomes positively charged. And loss of electrons always means cation. And what are cations? They have positive charges. So that's why the answer is Ca2 plus. Yeah, great job. Um, and we do have what's called a ionic compound. So I'm going to quickly cover this. Um, but basically what it is that compounds can be formed by two ions, a cation and an anion. This works because they have positive and negative charges. So these are called ionic compounds because they're compounds formed by ions. So Ca2 plus and O2 minus forms CaO, Mg2 plus 2Cl minus forms MgCl2, K plus I minus forms Ki. And this happens because K has a positive charge and I has a negative charge. And this comes from, the ions that tends to lose or gain electrons. So that's the basic of ionic compound. But let's look at this question. So calcium oxide and water reacts to form calcium hydroxide. So what is the formula of the product? Well, I do have this written down on the right here. So calcium oxide is CaO. Water is H2O. And this actually forms CaOH2 because calcium associates into Ca2 plus. And then it also forms the hydroxide ions. So that is why calcium ions with hydroxide ions, they form CaOH2. That is why the answer is B for this question. And OH has this subscript of 2 because hydroxide ion has a charge of 1 minus. To match that, we need 2 hydroxide ion since calcium ion has 2 plus. That is the basics behind this. So I hope, yeah, this makes sense for everyone. I know this ionic compound can be quite confusing, but I hope you guys understand what an ion is, what our cations and anions are. So yeah. Since today is the last day of chemistry, I wanted to cover a little bit more. This will be pretty short. All of these are reviews. So we've first talked about matter, remember? And matter can be separated into pure substances or mixtures. And we've talked about multiple separation methods like distillation, filtration, all of those are separation methods. But remember that mixtures can be homogeneous mixtures or heterogeneous mixtures. Homogeneous mixtures have the substances evenly distributed. So, like salt water, salt dissolved in water, salt is evenly distributed in water, but it's still a mixture between salt and water. We have mouthwash, alloys, and we also had, heterogeneous mixtures when it's not properly mixed. So things like pizza, salad dressing, landfills, those are heterogeneous mixtures. But now we can separate these mixtures into pure substances. And pure substances can be separated into elements or compounds. So compounds are like water, sodium chloride, carbon dioxide, where there is more than one type of atom, but it's not really a mixture. It forms a compound. It's a molecule. All of these are compounds. It has more than one atoms attached, but it's still the same kind of compound. That's why it's the pure compound. We also have elements, pure elements, which are just one type of atom, like oxygen, hydrogen, potassium. All of these are just one type of atom. That's the pure element and a pure compound. Those are all examples of pure substances. So this is a quick review of matter, and let's end off today with, uh, I don't think we have much time to finish off in osmosis, so I think this will be the end for today. So today we learned about, acids, bases. We've talked about strong acid, weak acid, bases. We talked about the litmus paper test. So first it was about acid, and then we talked about strong and weak acid, and then we talked about the litmus paper test. And then we also learned today about neutralization reaction. And we also talked about balancing chemical equations. And we talked about electron shells and ions. And then we ended off with talking about a recap of what matter is. So, yeah, today we learned a lot. We covered a lot today. But do you have any questions for today before we end? So, do you have any questions for today?
No.
You, yeah, any questions? Or if there are none, that's also okay. Um, yeah, if there are no questions, I think next week we will be moving on to sort of biology and ecology. So this was the sort of end for our mini chemistry session. But next week we will learn about plants and animal cells and photosynthesis and respiration. So next week, actually, I will be presenting. Um, some other students will. So yeah, you can be excited for that. And if final questions
Devin,
before we go, yes.
Devin, please. When you say something is neutral, what does it mean?
Oh, what does it mean when I say neutral? Um, let me go back to that slide. Um, are you talking about neutralization reaction? Or so it's okay, you might be talking about neutral here. So neutral has a pH of 7. That means it's not an acid and it's not a base. Neutral is exactly in the middle. And when acids and bases combine, they form a neutral compound. So neutral compounds like salt. So if we go back to neutralization reaction, acid, which is acidic, and we have base, which is basic. And when they combine, they form salt and water. And these are both neutral. So neutral just means there is a pH of 7, there's no acid, no base. So yeah, does that
Okay.
make sense? Yeah.
Okay.
Okay. Are there any other questions for everyone? Okay.
No. Are you sure? So you understand everything? Eh. Please ask questions, please. Ask questions. Yeah, if you have questions. You have a question. Yeah, hello.
Yes.
Yeah, Jim. Okay, so they said they don't have question, but if you have some for them, then they are ready.
I think I already asked a lot of
Okay.
the slides. Yeah. So I think that's good enough. So yeah. But
So
I was just saying, is today's topic too difficult or um it's okay, or I just wanted to ask the students.
okay, student, please. JB wants to know how did the thing go? Is it okay? Are you comfortable? Yes. How did it go? It's okay. So those who request for the acid date and then salt, are you okay? Yeah. Are your problems solved? Okay. So they said they are okay for now with the acid date and salt. So next week, what are we going to treat?
So yeah, next week we will be learning something different. It's plant
Okay.
and animal cells. So yeah.
Okay. So if I can they are what? They are going to study about plants and animals. That is the living cell. Okay? So please, break what? Get ready for JJ. All right? Okay. Do you have any concern, any question, any contribution towards next week lesson? Okay, okay. So we said that is okay.
Okay,
Yeah,
yeah.
okay. Next week lesson.
Yeah, thank you for letting them know.
Thank
And
you too.
um
Thank you too.
yeah, I'm glad that they understood I it was okay. And yeah, if there are no questions, then I will see everyone next week then.
Okay, so JB said you're seeing.
All right. Yeah. Bye, everyone. I'll see you next week and learn about plant and animal cells. Bye. Bye, everyone.
Yeah.